In this video, we're going to cover regression using a number of different algorithms and then evaluate the effectiveness via error on all of them. We're going to be using the mtcars dataset because it's a decent data set. It's fairly small, but it's a decent data set in order to get the point across by using these different algorithms. And the algorithms that we're going to be looking at is univariate and probably univariate linear regression, followed by the stepwise linear regression, spline, Mars, and then Loess at the end of it. And we're going to be able to see what's the effectiveness from the minimal error that each of these are producing in order to compare which one of these algorithms is the best for us. And so again, we're going to be looking at mtcars, but we're going to be predicting the miles per gallon when given the independent variables, a range of independent variables for each of these. So to get started, we're going to load up a couple of libraries by first installing these libraries. The CA tools one is going to be for sampling. The core plot is going to be for determining the correlation of each of our independent variables to our dependent variable, followed by metrics, so we can use RMSE, because in this tutorial, we'll be looking at the RMSE, a more standard way of determining error. Followed by the OLSRR for multivariate stepwise regression. So for stepwise, we'll be using this one. Splines, the library to perform splines, and then Mars needs the ERF library package. Once we have all of these installed, we're going to load these libraries. And I have here, just if you're following along with the code, I have them labeled there so you know which one is which. So once you load the library, then we can get on to preparing our data. In this example, we're going to be looking at cleaning up the data. So it's split into training and testing sets. Before in a previous example, we just used the straight up full mtcars, but in this one, I think it'd be better if we have training and testing sets just to get into the habit of doing that. So let's do that by preparing our data. We're going to set the seed to 1, 2, 3. You can set it to whatever you'd like, but if you're going to follow along in this tutorial, let's have the same seed set. So I'm going to set it to 1, 2, 3. I'm going to do a sample split on mtcars. So I'm going to be doing sample split. I'm going to be splitting my data, and you should do the $sign of a column. In this case, we're going to use the column that we're going to be predicting. So $MPG. We're going to do a split ratio of a 3 to 1. So we're going to do 75% of it is going to be our training set. And then we're going to just write whether or not it's a part of our sample directly into mtcars. We're creating a new column there called sample. After that, we have the training set. We're going to set that to whatever was true. So 75% of it, approximately 75% is going into train. And then the remainder is going into our testing set. So when you run this, you'll have a training and testing set that we can use in order to build our model and then evaluate it. Next, because we're dealing with a linear regression, and I'll run this just to make sure everything is fine. To make sure that we have the variables that we want, because we're doing a linear regression, we need to first establish correlation. So with correlation, I think an easy way of doing this with so many variables is by using core plot. So I'm going to pass in mtcars into core. This is going to give us a correlation matrix right here. And we're going to use core plot and output it there, where we're specifying that the method is number. This is going to give us the number as opposed to just like kind of a circled heat map. So let me run this. From here, everything on my computer seems a little bit scrunched up. So I'm going to click this little pop-out button here, and it's going to bring up my correlation map and make it a little bit larger. From here, we can see, again, we're going to be predicting MPG. So we can just go straight down this line looking for columns or features that have a strong enough correlation for us to use. Again, our correlation threshold ultimately will be either greater than 0.5 or less than negative 0.5. So we're looking at cylinder, that's a good case. Displacement, we have HP, we have DRAT, weight. This one is below, so it's in that it doesn't actually meet our threshold. VS, AM, the rest we can look at, but we're looking to see which one fits into our threshold. So now that we have the correlations, we can go back into our code and then pull out the features, the columns that actually meet our threshold for predicting MPG. MPG based off of these features. Okay, so we're going to first do a multivariate linear regression. So it's just a linear regression of multiple variables. And by following those features that had a strong enough correlation, greater than 0.5, we have a couple of these features that I would like to throw in as our independent variables. So we have the cylinders, displacement, etc. And we're going to be predicting MPG based off of that. Just before doing that, I'm going to create a actual variable, and that's going to store the actual values, the values of MPG. So I'm going to take my testing sets column of MPG. I'm just going to make this actual. We're going to use this later on. So first, now that we have what our formula, this is our formula, and we're going to be training it on our training set, we're going to do LM on our formula and our training set stored into LM model. Then we're going to predict. So we're going to store our prediction in LM prediction. And we're going to call the predict function on that new model that we just created, passing in the testing set. We trained it on a training set, and we're going to evaluate it on a testing set. So now we're going to predict it. We get the prediction there. And now let's evaluate using the root mean squared error, the RMSE. That's going to give us a value that's about the error of our model. We're going to compare our predicted values versus the actual values that we generated up here. So this one is of test. These are the MPGs of test, so actual. And then what we thought the MPGs should be, or we predicted the MPGs should be from our model. So when I run this, you're going to get a root mean squared error, an RMSE, of about 2.83. So this is our base. For using all of these variables, we now have a base. Let's go down to a stepwise. So this should be stepwise. So our stepwise regression has a couple of directions that we can go. We can either go forward, we can go backwards, or we can go in both directions. First, let's start out with the forward. We're going to take our LM model that we built in here. We're going to do it with a forward elimination. So we're going to call this OLS function. That's from the package that we loaded up. And Stepwise is going to go forward, adding new features one at a time in order to get a better R-squared value. So we have our LM method model that we created up here. And we're going to just set details equal to false. And then so from here, we're going to store this model's output into Stepwise for now. And then we're going to predict using this model, because it has a model, this object here, we have to call the $ model to extract the model. And we're going to then evaluate it on our test. And we're going to store those values of our prediction into a vector called Stepwise Prediction. And let's just go ahead, just like what we did up here, we're going to output the RMSE prediction. Now we're going to print out the RMSE based off the Stepwise Prediction. And again, passing in the actual. We're going to just cat it out again. We're going to do the same thing. Notice up here we did it for forward. Let's now do it for backwards. And then finally, we're going to do it in both directions. So when we run this, we have one model, we get the RMSE. The backwards model, we get the RMSE. And then both, we do the RMSE. And when we run this, we should get 3 different values up here. This will allow us to get different error rates for the different types of algorithms based off of the linear model that we created. We're going to be comparing the error rate that we get for each of these with the error rate that we got with just this simple linear regression. So here we had 2.8, but when we went forward, we got 2.9. Okay, well, what about for going backwards? Well, backwards actually had a 2.8 also, but it's slightly smaller than this one. So right now, going backwards was a better algorithm. And then going in both directions, we had 2.98, which was the same as forward, but worse off than our backwards model. So right now, our best model is this one, our stepwise backwards. So again, backwards is you throw in everything and you slowly remove the different features that are not adding to your model's accuracy or lower error rate. So the next one is splines. So splines, if you remember from before, splines is creating all these let's say jagged lines. It's finding different LMs, linear models for segments of the data continuously. So now we're going to use our splines library that we imported before, but we're going to call the smooth spline function, and we're going to predict the training sets MPG. That's going to be on our Y. The X is only going to be a single variable, because splines can only take one single independent variable to predict on. So it's going to break up the weight and then try to estimate what that y is. And in this case, we're going to take the variable, the independent variable that had the strongest correlation. So if we scrolled up a little bit, you would see that the weight, the WT, had the strongest correlation to MPG. So that's why we're using it here. You can actually use any feature you want, but in order to give the best model with the lowest error, we probably want to use the correlation, the feature that has the strongest correlation. So in this case, it's weight. Okay, so we're going to just do RMSE on this, but in what this object that returns, it has a number of different attributes inside of it. So we're going to use this output from our prediction. We're going to call its y the predicted y. So that's why we're doing the $y. This is necessary in order to get the vector of predicted values. And then we're going to, again, pass in actual. So now when we run this, we're going to get a RMSE of 8.28, which is significantly worse than the errors that we got, the RMSEs that we got up here. So we can kind of discredit, we can kind of move on from splines. But splines sometimes have different cases where we're going to see a better error. In this case, it did not improve our model. The next one is something called MARS, so the Multivariate Adaptive Regression Splines. This allows us to have multiple splines, so we can have multiple variables inside of our independent variables, not just one. So we're going to use Spline and the packages for ERF. We're going to predict the MPG, but we're going to pass in the same variables that we had up here in our linear model and our stepwise. So the formula is exactly the same. We're going to use our testing set, and we're going to call ERF to do our MARS multi-splines. And then so we're going to store that model in a variable called MARS model. We're going to predict with that model, and we're going to store the prediction there, and we're going to compare it to the actual, so we get an RMSE. Let me run this. There we go. So we have 2.7. This is so far, this is the best model that we've had, the one with the lowest error. What MARS does is it creates a number of different lines going with our different variables or features that we have here, unlike this one feature set that we had there. Okay, lastly, we've learned of a nonlinear regression one called Loess. Loess is very simple, just like LM, but just to compare and then to show you some things to extend our use of Loess, is we're going to pass in the same formula that we have up here. We're going to try to pass it in Loess. And let's see what happens. So we're going to call Loess instead of LM. We're going to then do a prediction and then get the RMSE. When I run this, we're actually going to get an error. The reason why we're getting an error is because of degrees of freedom allowed inside our Loess. It's really limited to a max of 4. So we should reduce our number of independent variables to 4 or something that's less than 4. In order to do something like this, one thing you'll see is that there's a couple of errors that you'll get. We saw before we can do MPG on a single one, but now we want to actually do we want to get to more complex ones. But if you try to do just this Loess method on one feature, so 1 to 4, MPG on what we found out to be the one that had the strongest correlation, which was weight. If I take this out, you'll see that you'll get an error or some NA values. The NA values means that there's some NAs, some not available or not actual numbers inside of it. In order to make sure that you can get actual values coming from the Loess function, we need to do something that's going to do some extrapolation, because by default, Loess is doing something called interpolation. Well, we don't want interpolated data because that's going to give us NAs. What we want is extrapolated values. So we're going to pass in a surface that's called direct into Loess, and that will allow us to use one of these features or a subset. In this case, we're only going to be using one of these, the best one, to be able to compare our model above. So we're going to do Loess MPG tilde weight, and specify our data. But we're also going to specify the control. We're going to set the control to a direct surface. So we need to have what you see here. This will then allow us to predict MPG with no problem when given the weight. So we pass in that surface, that direct surface. We do the prediction on our Loess model that you see here, given our testing set, and here's the RMSE. Let me run this. And then so now we have an RMSE of 3.12. Let's compare all of these error rates. So we have Loess of only weight as 3.12. We have Mars of 2.7, which we know was the best. When we tried to do just a one straight up comparison of Spline of when given the weight to predict the MPG, we had a higher value of 2.8. Compared to this, Loess with this new direct surface is significantly smaller. Okay, let's scroll up. And again, we had from our Stepwise, this was the best Stepwise, but later on we found out that this Mars actually produced the lowest error of all of these. So that's going over a number of different algorithms. Just to recap, we have linear regression, which we first established a correlation. We only use variables that had a strong enough correlation for linear model. And then we did stepwise to eliminate some of the, to eliminate an ad, but really to eliminate the features that we suspected should be good to predict our MPG. And then we use Spline to create a prediction that's kind of like jagged, but on one variable. Then later we did Mars by calling Earth, and we passed in everything. And then which gave us the lowest error model. And then we used Loess, but Loess has a limitation of 4 features. So we wanted to use at least one between 1 and 4. We picked the one that had the highest correlation, which was weight. And then we specified the control of a direct surface. So we were able to actually get a value here. And then all of these, except for our spline, had a comparable error rate with splines actually being the highest. So don't forget the steps, the appropriate steps to be able to do all these kinds of regression. And it's good to be able to compare each of these models by using our error.